present you the work that has been done on this CLC project. And I would like really to thank DBC for hosting this annual event. To continue the journey of this CLC project, so we are speaking about the R&D. Basically, it was a production by CINOA and IFPN in their respective laboratory. And then Inve and Aurélien speak about the oxygen carrier. And now we really enter the project management part of the CLC. So the part I will speak about is mainly the FEED, front-end engineering design. And I will speak also about the pre-FEED or PDP, process design package. And Total Energy was in charge of this part of the project. And I would like already to thank two people, Madi Yazdan-Pana and Vincent, who were really the people in charge of this part of the project, the FEED, because as Patrice, I arrived, I took the train when it was already started, and I arrived 2 years ago in this project. So for the agenda, I will recall the timeline and the scope, and speak about the main challenges we face during this FEED, the outcomes, and some learnings. So the FEED is like the front-end engineering design, is really converting all this R&D project into an engineering so that we can do the EPC after that will be presented by Xingbei Liu from DBC. So we are really converting the conceptual and the R&D design that has already been presented into the basis for the construction of the plant. So you see that the FEED has been done in 2021, basically for 1 year. And it's part of this project management which has been coordinated by CINTEF. So when you look at the CLC project, you have first the core of the CLC is the reaction section, and that was basically the pre-FEED or the PDP, process design package. And when we speak about the FEED, we speak about the ESBL or inside battery unit, plus the site integration into the site of DBC in Neyang. And after, we will have a presentation on the EPCC, which is the ISBL and OSBL. So, first challenge for this FEED, it was the organization. First, the contract for the FEED was awarded to Gouraud, and they used two offices, one in Europe and one in China. And furthermore, it was during the restriction time, so mainly all of the meetings were done remotely, with some time difference between Europe and China. So I let you imagine there was, basically we had half a day every day to be together. So it was quite challenging, so we achieved to find some time to succeed in this field. The second challenge is really, as we already talked to you, the two intentional configuration. It's not easy to put two configurations in only one unit. When you visit it this morning, you see some big plans to separate the two configurations, and they are quite. It was interesting to do it. The third challenge is more about the parameters. It's a test pilot demo unit. We want to be able to change parameters to have as more data and to learn as much as possible on this CLC unit. So the first parameter we want to change is the power. We want to go from 50 to 100%, go from 2 to 4 megawatts. So we have different devices to inject feed at different flow rates. The second challenge is the oxygen carrier. So as Eileen just told, we choose ilmenite. And this ilmenite had different specificities. Patrice speak about the recycling in the European configuration on the air reactor. We want to see different states for the oxidation state of the ilmenite. Basically, Professor Lee said that we will have one full oxidation in one pass, but if it's not enough, we want to have the possibility to oxidize further the ilmenite. Then we want to play with the oxygen transfer capacity. We call it the range between the oxidation and the reduction. And another parameter is the density of the ilmenite. This density, the ilmenite has got some fresh properties because the fresh is at 4,800 kg per meter cube. But after a few cycles, when it gets oxidized several times, the density changes. So it will change the way we will control the imbalance. So this is challenging as well. And then we will, the third point is the different fuel that we will use. You see that we use natural gas for the startup, but then for the operation we use lignite for the Chinese configuration and petroleum for the European configuration. So all that need to be taken into account. And furthermore, we want to test also some recycling flue gas to dilute, for example, the contaminated flue gas. And so we installed some possibilities to inject CO2 at the bottom of the fuel reactor. So for that, we study many cases during the field, 23 in fact. So, and the last challenge is really to say that it's the first of a kind. So we have some experiences on FCC for refining and CFB in the power industry. But this is really new, this CLC, with real change with the L-valve specificity and the oxygen carrier specificity. And we wanted also to have a design for this demo unit that really represents the high-scale unit. We need to have a size not too big, but big enough so that we can have some data for the next stage, which will be the industrial stage. So we want to be able to measure the carbon capture efficiency and to have a unit with as low as possible heat loss so that we can do the autothermal mode. So the outcomes. So the first is we outcome with lots of documents during the fields, mainly we speak about 235 valuable documents on the HSE part, on the project management part, and on all the technical parts. So mainly valuable documents. Then, if I speak mainly for the process safety, we use some references from the industry, references from Total Energy for the process safety, and references from DBC for the operational safety. During the pre-feed and the feed, we did hazard identification, so we imagine all what can happen on this unit, and what can happen, and what mitigation measures we need to implement to overcome this potential risk that can occur in this unit. And we did the hazard for sure, hazard and operability, and low layer of protection. So this hazard was completed during the feed and was updated with the few modifications that we have done during the EPC stage. So the main outcome were some PFDs for sure and some PNRDs. And we produce some data like the process data sheet, the mechanical data sheet. And one of the questions that we asked is that really the size of all the equipment, we want them to be not too big, but not too small also that they are easy to manufacture. When you have a too small vessel with refractory inside, sometimes it's not easy to manufacture, so you have to find the right size so that they can be easily manufactured. Then, when you look about the pilot, you want to have as much data as possible, so you want to have as many sensors as possible. So you add some many sensors of temperature, pressure drop everywhere. Compared to an industrial unit, we will have much more sensors in this demo unit. So you have the scale, some nozzles everywhere, some sensor everywhere. So it's really necessary to go for a 3D so that you can see all the compactness and how can the things can handle together. Then you discuss about the constructability. So we hopefully we had during the COVID time we had some Chinese colleague in Gouraud, in Total Energy, in DBC that could do the site survey for the field and could help us to do some design or some show some places where we could put the crane and how we can build this unit. So the approach that was chosen for the fabrication, it was a stick build approach. So reactor structure, and we built this 44 or 50 meter high unit that you saw this morning. And then what about the learning? So it's small in size compared to an industrial unit, but it's much more complex in fact, because it's first of a kind. You need frequent startup and shutdown when you are dealing with the pilot, and you need this autothermicity, and you need these two interchangeable configuration, the Chinese and the European configuration. Furthermore, we need to be very agile because during the feed we had some question about the modeling. So we went back to do some modeling tests to answer some questions that were raised during the feed. So hopefully we had some very reactive people in Tsinghua and IFP also to answer this modeling question so that we cannot stop the process of the feed. And finally, I really repeat, we produce lots of documents that in which we used oil and gas and power standards, and also we used all the safety aspects were taken into account. And this document could be used for the EPC or even further for an industrial step further. So, and all of that mainly was done in a very fast. It took 1 year, and it was also what I wanted to say also is that we had very constructive attitude with the Chinese and European, and all of that great discussion could this make happen, and the feedback was able to be done. And then by the end of the year 2021, we could do the FID, or final investment decision, to go on for the next part that would be the EPC. So thank you very much for your attention.
Thanks very much for Vincent's presentation. Any question? Any question? Yeah. Okay.
Thank you, Vincent, for the clear presentation. So at the end of this feed, in terms of modeling, we have a tool that we can use or reuse for further steps, especially during the testing phase that we are facing now. It's something we are going to calibrate or to check.
That we used the model that was developed with the Aspen Plus model, and this model was done to design the 3 megawatt unit. And this model could be also used for the upscaling after for the industrial side.
Okay. Any other question? If no other question, let's thank Vincent again. Yeah. Thank you very much for your excellent presentation. Yes. So next speaker will be Vincent from EC company. The presentation is the introduction to EPCC construction. Let's welcome Vincent.